folks, welcome to my YouTube channel. This is the grade 11 paper 2 chemistry revision. For the final examination, I'm going to do the possible question. I'm just taking question from different question papers. Now it says a chemical bonding. I'm going to start with question 2. A chemical bonding is defined as a mutual attraction between two atoms resulting from a simultaneous attraction between their nuclei and the outer electrons. Answer the following question in terms of the chemical bonding. Now 2.1, it says define the term electronegativity. The electronegativity definition, guys, stick to the exam guideline. It says it's a measure of a tendency of the attraction of electron Now 2.2, it says use the electronegativity to explain which of the following atom would likely be a negative ion. So if you have a metal and a non-metal, it's going to be a non-metal. So what do you need to do in this question? You need to put their electronegativity. The electronegativity of aluminium is, and the electronegativity of sulfur. So you look at the periodic table, we have a sulfur here, it's 2.5, and aluminium, it's 1.5. So it's 2.5 and 1.5. Therefore the answer the answer is going to be sulfur, because it has the highest electronegativity than what? Than aluminium. So the one that has a highest electronegativity, it's going to be a negative ion. And you can see it's a non-metal. This one and this one is a metal. It's going to be in a metal. Now it says 2.3 shows by means of electronegativity what type of bond will form between the elements of each. So the bond, guys, you calculated the electronegativity difference, right? So calculating the electronegativity difference here, so what do you do here? You must know the electronegativity of so magnesium. So you say the change in electronegativity. So you start with the big one. You say the bigger electronegativity minus the smaller. It's oxygen and magnesium. So you're going to start with oxygen. So it's going to be the electronegativity of oxygen, because it's bigger, minus the electronegativity of magnesium, right? It's going to be, forgot now, it's 3.5 minus 1.2, 3.5 minus 1.2, which is, it's going to be 2.3. So if it's 2.3, that means that this bond that exists between these two, it's therefore the bond between the magnesium bond is ionic. It's ionic because the electronegativity difference, it's bigger than 2.1, right? It's bigger than 2.1. Let's check here. Let's check here. So if the electronegativity is bigger than 2.1, it's ionic. The bond between that, it's ionic. Let me take this. The bond is ionic there. So let's just put it here. It's going to help us. So the bond is ionic because the electronegativity is greater than 1. Let's go to HCl. The H and the Cl, I think the one that is going to be bigger is going to be the Cl. The Cl is 3, the chlorine, and the hydrogen is 2.1. It's 3 and the 2.1. So you do the electronegativity difference, the change, and the electronegativity between the chlorine and the electronegativity and the hydrogen. It's, I forgot now. It's a 3 and a 2.1. 3 minus 2.1 is equal to 0.9. So here we can conclude that the electronegativity, the bond, the HCl bond because it's less than, let's look at there. You must note these. It's less than 1. Do you see? It's less than 1. It's a weakly polar covalent bond. So it's a weakly polar covalent bond. Guys, you must memorize this thing. Memorize this thing. It's very important. So since the electronegativity difference is what? Is less than 1. Now 2.4, it says the valence shell electron repulsion theory is used to predict the geometrical shape and define the valence electron. Guys, stick to the exam guideline when it comes to the definition. You need to know the definition. It's the electronegativity and the valence electron, even the chemical bonding definition, right? Now it says 2.5, draw a Lewis structure. Okay, 2.5, draw the Lewis structure of oxygen. The Lewis structure of oxygen, guys, is just one oxygen, and oxygen is in group 6. It's going to have 6. 1, 2, 3, 4, 5, 6. It's going to be like that. And for phosphorus, phosphorus is in group 6 as well. It's the same as oxygen. Do you see? No, it's not in group 6. It's in group 5. It's going to have 5. Phosphorus is going to have 5. You put P, and then it's going to have 5. It's going to be that. Guys, you can put the dot, you can put, and then now it's HOCl. So you start with the oxygen, and then the oxygen, it has 1, and the hydrogen, it has 1, sorry, and then the oxygen, it has 6. And then it's going to be oxygen. Here's the oxygen. It has 6. Right? And then let's take the chlorine. Chlorine, it has 7. It's going to share 1 because it needs 1. It's going to share 1 and get 1. So it's going to be like that, guys. For that, it's very important, guys, to draw the Lewis structure. 2.6, it says how many bonding pair of electron are there in a trigonal planar. The trigonal planar, guys, it's when it has let's say we have the trigonal planar is the shape of this one, guys. It's the BF3. It's like that. This is the trigonal planar, right? The shape of this one is a trigonal planar. The trigonal planar, it has three bonding pairs. So it says how many bonding electrons it was pair bonding 3 electrons. The answer here is going to be what? 3, because it's 1 pair, 2, 3. So it's 3 bonding pair. They're not asking electron each. So if they were asking how many bonding electrons, not a pair, it was going to be 6, 2, 4, 6, right? The answer there is 3. And then it says indicate the valence shell electron repulsion shape. What is the shape of this one? The shape of this one, guys, it's like this. It's a C with a chlorine, 4 chlorine. There's a chlorine. And there's a chlorine there, a chlorine there, a chlorine there. So this one, if it has 4 bonds, it's what? It's tetrahedral. You must know the shape, guys. And this one I've already explained. It's a trigonal planar. It's a trigonal planar. Right? And SO3, it's a band shape. It's a band shape. It is a band or an angular shape. You don't have to draw the structure, guys. You don't have to draw these. I'm just showing you. It's an angular shape. I'm going to show you it's band or angular. The SO3, it's like this. It has a double bond and a double bond, and oxygen, and the lone pair there. It's bent. Right. 2.8, it says hydronium ion is formed when acid is ionized in water. Right, we know that from acids and bases. What type of bond forms when hydrogen ion and water molecules? So this one, we call it, it's a dative covalent bonding. It's a dative covalent bonding, or it's a coordinate covalent bonding. 8.2.1 says use the Lewis diagram to show the formation of hydronium ion. The Lewis diagram to show so guys, this is not the answer. It's water plus the hydronium ion gives you the hydrogen ion and gives you the hydronium ion. This is not the answer. They want the Lewis structure, not like this. So the Lewis structure for water, it's going to be that it's a band-shaped water like that. It has two lone pairs, right? Plus the hydronium ion. Here's the hydronium ion, and what's going to happen? This hydronium ion, it's empty, right? So it's an empty s orbital, so it's going to go in one of these lone pair, and it's going to get the share, and it's empty, so it's an empty s orbital, right? It's going to get the share of these two electrons, these ones or these ones, doesn't matter. So this is what is going to happen. Let's say this, it stays there, and then you have the hydrogen there. So this becomes a what? It becomes the hydronium ion, right? You must know even for ammonia, for ammonia, it's ammonia plus the hydrogen ion. It gives you the ammonium. This is not the question, guys. I answered the question. This is the answer of the question, right? So the ammonia, it's like this. It's like this. Guys, it must be a Lewis structure. Don't draw the bond like this. The three bonds, these bonds here. No, don't do that. And the hydronium ion, so it's going to end at the lone pair there, so it's going to go to this lone pair and get the share, so it's going to be something like this. It's going to be like this, the hydrogen, and there's that, there will be that hydrogen there, so it becomes here, it becomes the ammonium, it's NH4 plus, and then it's NH4 plus like that. Let's go to the next question. Question 3, the one that involves the intermolecular forces and the shapes and everything. Now it says, a group of grade 11 learners investigate how the intermolecular forces affect the boiling point of different substances. They recorded the following results. So we have here different compounds here. We have water, we have acetic acid, we have benzene, we have a chloroform, right? So we are given their boiling points and melting points, right? So if you look here in these molecules, the one with the greatest boiling point or melting point, that means it's the one that has a strongest intermolecular force. If you look here, let's start with the boiling points. The one with the greatest boiling point here, it's going to be the greatest boiling point is going to be the acetic acid, right? The acetic acid, and even the melting point, the one with the greatest boiling point here, if you look here, it's still the what? The acetic acid. That means the acetic acid has a stronger intermolecular force, right? Stronger intermolecular force. Remember, the intermolecular force is directly proportional to the boiling point or the melting point. Greater intermolecular force, that means greater boiling point, greater melting point, right? So if you compare these two, this one is they have the hydrogen bonding, these two, and these ones, these two, but between these two, this one, it has the London, and this one has a dipole, but their boiling point, they tell us something differently. So the one with the melting point, highest melting point, is this one. Negative is smaller than the positive, so this one, it has a more boiling point than this one, and the melting point and the boiling point as well. right? So this one, these two, this one has a strongest intermolecular force than this one, and between these two, this one has the strongest intermolecular force than this one, right? Now let's answer the question. Define the term boiling point. You must know the boiling point, guys. Okay, 3.2, it says explain why water has a higher boiling point than chloroform. So we are comparing these two, right? Comparing these two. So the first thing that you need to do when you compare the different compounds, so you need to talk about their intermolecular force. So you will say in 3.2, the answer there in 3.2, you will start, you will talk about the water. You will say water has a what? A strong hydrogen bonding, hydrogen bonding, hydrogen bonding or hydrogen bonds. They have hydrogen bonding. Okay, let's leave it like that. And then you say the chloroform, guys, the force that is here, it's a dipole, right? It's a polar, right? So if you have another chloroform here, the chloroform, it's a polar molecule, right? It's a polar, so it's a polar and polar. So you will say chloroform, has a weak dipole bond, right? As a weak dipole bond. So now you have compared their intermolecular forces. So you have 2 marks. So you are only left with 1 mark. So what are you going to say now? You will say hydrogen bonding is stronger. Now you're comparing the strength is stronger than the dipole bond, right? And then lastly, you talk about the energy. The one that has a stronger intermolecular force needs more energy to overcome the intermolecular force. So you will say water need more energy to overcome the intermolecular force, right? So guys, this is 3 marks, and this is 1 point stating their intermolecular force, and then you compare them, it's 1 mark, and then you talk about the energy, it's 1 mark. That's 3 marks, right? 3.3, it says in the diagram above of molecules, it says in the diagrams of molecules in the table above, as a guide, explain why chloroform has a lower boiling point than benzene. So now we're talking about the chloroform and the benzene, right? The first thing as well, you need to talk about their intermolecular force. Remember, this one is what? Is London. And this one is what? Is a dipole. But this one, compared to this one, according to their melting point and boiling point, this one is stronger, even though it's London, right? Even though it's London, what makes it this one to be stronger is the surface area. Do you see this one? It's bigger. It occupies a lot of space. It has a greater area. This one, it has a smaller area. So what are we going to do? We're going to say both. Okay, so what are we going to do in 3.3? We're going to say benzene has a what? A London force. And then we'll say the chloroform has a dipole dipole force or bond, right? And then you compare the strength of the intermolecular force, right? But before, another thing that you need to compare by, when it comes to this one, since they differ in terms of the boiling points. This is why it has the lower boiling point. This one, the chloroform, why it has the lower boiling point. So you say benzene, since benzene, it occupies a lot of space, you say has a what? Has a larger surface area. Than what? Than chloroform. And then what you need to do now, you need to talk about and then you talk about the energy. And then you say benzene has a stronger, so we concluded that benzene has a stronger intermolecular force than chloroform. And then here, remember what you spoke about? You spoke about their intermolecular force. You mentioned one intermolecular force and one intermolecular force. And then what makes them to be different? And then it's what? It's the guys, both they have London. Since the chloroform has a dipole force, it has a London as well. So their intermolecular force, they're almost the same, but they have a difference in surface area. This one has a larger surface area than this one, and that's why the boiling point of this one is bigger, because of the larger surface area. And then you say benzene has a stronger intermolecular force, right? 3.4, it says study the following substances. We have chlorine, hydrogen chloride, and chlorine gas, water, carbon dioxide, hydrogen fluoride, and magnesium chloride. Which one of the following have the highest intermolecular force? Always, guys, the one with the highest intermolecular force here is an ionic compound. It has to be an ionic compound. The ionic compound here is the last one, which is the what? It's the MgCl2, right? And then the one with the London, guys, is the nonpolar. This one and this one is a nonpolar, so it's a what? Cl2, because these are the nonpolar. So the nonpolar has the London and the CO2. The one with the hydrogen bonding, it has to be the hydrogen fluoride. Remember, the hydrogen bonding, it has to be the NOF, the one that has a nitrogen, oxygen, and fluoride. So it's going to be water and hydrogen fluoride. The one with the dipole, it's the HCl, right? It's the HCl, right? Now, it says here, for the following compound, state whether the molecule is polar or a non-polar. Okay, the oxygen, guys, it's a non-polar, but you don't just say it's a non-polar. You need to okay, this one is a non-polar. Why is it a non-polar? The oxygen, it has a double bond, and then the net dipole moment there is equal to 0, so they equal attract the electrons. So this one, the net dipole moment is equal to 0, because this force and this force are equal in opposite direction. Therefore, it's a what? It's a non-polar. Go to my other video, guys, when it comes to the polarity here. So this one, the ammonia, it's a polar. So the net dipole moment there is not equal to 0. Net dipole moment is not equal to 0, therefore is what? It's polar. So this molecule is what? It's polar. Look at my other video, guys, when it comes to this. Now it says the molecules NH3 and PH3 have a similar shape. So their shape, it's a what? It's a trigonal planar. Yet pH3 has a much higher vapor pressure than at STP than the NH3. So if it has a higher much vapor pressure, so this one has a higher vapor pressure, that means this one has a weaker intermolecular force than this one, because the intermolecular force here is the hydrogen bonding. This one, it's the London. So how are we going to explain this? Okay, so the question, it says define the vapor pressure. Guys, you must know the vapor pressure definition. Now 3.6.2, it says explain the difference in vapor pressure between the above mentioned molecules by referring to the type of strength of intermolecular force of each. Guys, as I've mentioned, you need to state the intermolecular force between the two. So 3.6.2, the first thing you'll say, pH3 has a what? A higher vapor pressure. Has a what? A higher vapor pressure. Vapor pressure. It's not mentioned there. It says they have a similar shape, but yours has much higher vapor pressure. So this one has a high vapor pressure. Okay, I don't think that should be a mark because it's mentioned in the statement. Now the next thing that you need to do, you need to state their intermolecular force. You say the pH3 has a what? Has a London what? Force, right? It has a London force. And then the next thing you talk about the NH3, this one is a London, guys. It's a London, and this one is a hydrogen bonding. The NH3, which is the ammonia, has the what? The hydrogen bonding. And then lastly, you compare these two forces. You say the hydrogen bonding is stronger than the London. It's 4 marks. And then the last mark, guys, this is not a mark because it's already mentioned there that it has a much higher vapor pressure. So the last mark, these are the marks, 1, 2, 3. It's gonna be the fourth one, this one. So you will say the NH3 need more energy to overcome the intermolecular forces, right, than the pH3. Guys, that's the end of the question 3. I hope this makes sense. Question 4 on ideal gases and Boyle's law. Now it says the relationship between the pressure and the volume of gas investigated at 20 degrees Celsius. The results of the experiment are given at the graph below. If you look at the graph, this graph, it shows us that the pressure and the volume are inversely proportional. Let's look at, if we start with the high pressure, and the volume will be that. But as the volume decreases, the pressure increases. Do you see? As the volume decreases, the pressure increases. Do you see that? Right. Now, so it means that the pressure and the volume are inversely proportional, right, at a constant temperature. Right, now it says name the gas law that is represented by the results of the graph. So the gas law that is represented here is what? It's Boyle's law. It's Boyle's law, right? Boyle's law. So now 4.1.2, it says a gas mentioned 4.1 can be written as PVK, and K represents the constant value. Name the two conditions for K to which to be constant with a different pressure and volume. So it's what? It's temperature. They told us the temperature here, it's 20. Let me use the red one. The temperature, it's 20 degrees, which is its constant. And the second thing, it will be a mass, or you can say number of moles, or number of what? Of gases. Number of gases, right? Now, in 4.1.3, it says, what is it, guys? You need to be sure here. It's temperature and number of moles or any of this. Now, 4.1.3, it says, calculated the volume of the pressure at 300 kilopascals. If you're looking here, we're given the volume, which is 205, and the pressure, that is 59. So they said we should calculate the volume at 300. 300 of pressure. 300 of pressure will be somewhere there, right? Let's say the 300 is there because it's bigger than the 59, and then the volume that they want is that one, right? So this will be our initial, and this will be our 1, and this will be our 2 there. So I'm gonna do this answer 4.1.4. That's P1 V1 is equal to P2 V2, right? The initials, our initials is gonna be these ones, right? It's the pressure is 59 times the volume, it's 205, and the pressure here is 300. We times by the volume, which is the V2, and then our V2 is going to be, we divide by 300, it's going to be 59 times 205 divided by 300, the V2. So it's going to be 59 times 205 divided by 300. So the answer here, it's going to be a lower pressure, a lower volume, which is it's 40,32. The answer is going to be in kilopascals because we're given in kilopascals there. No, sorry, the volume, it's going to be dm3 because we're given in dm3. If it was the pressure, it was going to be kilopascals, right? Let's go to the next question, the last one. It says, in ideal gases and real gases differ under a certain condition, and name the condition where they deviate. Guys, always they deviate at what? At low temperature and high pressure. That's where they deviate, guys, all the time. They deviate at high pressure and low temperature. When they do not deviate, guys, they are same. They are the same at opposite of this, low pressure and high temperature. Now in 4.2, it says write down the mathematical expression and in symbols for the relationship between the variables, which is the variables, which are the variables is this one. What is the mathematical relationship between these two? The answer is this. So let me write the answer here. P is inverse. So when they say mathematical relationship in symbols, guys, it has to be this. Now it says name the gas law is investigated. We already mentioned that. It's Boyle's law. Right, it says explain relationship in 4.2.1 in terms of kinetic molecular theory. The kinetic molecular theory, guys, as you can see here, as the pressure decreases, as the volume of the container decreases, the pressure increases. But you need to explain it in terms of KMT. So when you explain it in terms of KMT, which is KMT, this is supposed to be KMT. 4.2.3, you will say as the volume of the container, decreases, the number of collision per unit area. The collision per unit area, guys, is the pressure, the unit area on the walls of the container walls of the container increases. So guys, this word here, the number of collisions, supposed to be collisions per unit area. So the number of collisions per unit area, guys, this is referred to what? Pressure, but you need to write it like that. Pressure on the wall decreases, increases, right? So it states this, guys, this is the relationship, but you state it in words, but in terms of pressure, you need to say it's collision per unit area. The pressure, guys, it's a force per unit area, which is it's a collision. The force is the collision per unit area on the container, right? Increases. So as the volume decreases, the pressure increases. You can see here, even here, the volume decreases, the pressure increases. There, guys, I hope I make sense by that. Cheers. Let's look at question 5. Question 5, it's an energy change. The energy change, now it says the bond energy for different types of bonds listed in the table below. So we have different bonds here, then there are energies. These are the energies, right? Right now, 5.1, it says define the term bond energy, right? You need to define the bond energy, guys. Check the exam guideline when it comes to bond energy. It says the equation for combustion of methane gas is given below, guys. This is methane in the presence of oxygen. It gives carbon dioxide and oxygen. So guys, we know this type of the combustion, as long as it's the combustion, it's an exothermic reaction. That means our delta H is less than 0. So there's an energy release, which is it's an exothermic, right? At 5.2, it says use the information on the table to determine the change in enthalpy. So when they talk about the change in enthalpy, they want the delta H for the reaction. And they give us the hint of the graph, that the equation that we're going to use. Guys, we want to calculate the delta H, and we anticipate and we know that the delta H is going to be less than 0, which is going to be a negative value because it's a combustion. This one, we're going to use that equation and use these bonds, right? Now in 5.2, guys, in 5.2, this is what we're going to do, right? So we're going to use this equation. We're going to say delta H is equal to energy bond breaking minus the energy bond forming, right? Okay, now the bond breaking, they're breaking here in the reactants. So we're going to start with this one and this one. And guys, this is a CH4. It's CH4, which is, it's this, guys. This is this. It's a methane, right? It's like that. How many of these bonds, the CH? It's 4 of them, right? Do you see it's 4 of them? We find that the CH4s there. So what we're going to do, we're going to say it's a 4 what? CH bond. Plus, we're going to the oxygen. The oxygen, it's like that. It's like that. And how many are they? There's a 2 in front. That means the 2 of them there, which is there. These ones, right? It's 2 oxygen bond. And then we close the bracket, and then we go to this one. So the energy release now is the carbon dioxide. The carbon dioxide, guys, it's a C as a central and a 2 oxygen. So how many bonds there? It's 2 CO bond, which is these ones, right? It's a 2 CO bonds, and plus we're going to the water. The water, guys, it's like that. We have this the OH bond. It's 2 OH bond. It's HO, 2 OH bond, right? It's 2 OH bond. Guys, that's a very easy one. Let's look at the 4 CH bond. The CH bond, it's 414 plus the 2, the oxygen bond, it's 498. It's 498, and then we close the bracket, we're minus, then 2, the CO bond. Where's the CO bond? It's 799. It's 2 799 plus the 2 OH bond. It's 460. It's 460. And then, and when you punch that in the calculator, guys, you just punch that in the calculator, it will give you negative 786 kilojoules per mole. Don't forget the units, guys, because you are given the units there. It's kilojoules per mole. So that's an answer there. Now in 5.3, it says refer to the question in 5.2 whether the energy is entirely released or absorbed. Give reason for your answer. So the answer in 5.3 is what? Is released. And then it says given reason for your answer. Reason for your answer, your delta H here. Your delta H here is less than 0. Or you can say your delta H is negative, right? So there's more energy released than absorbed there. In 5.4, it says, is methane a gas suitable for fuel? Answer yes or no. So methane gas is suitable for fuel. So yes, it's suitable for fuel. Alright, the methane is one of the alkanes, guys. It's suitable for fuel. The answer there will be yes. Question where there's an empirical formula and the molecular formula involved that you need to do. Right? So in this question, guys, it's always there in the question paper. High chances that it will be there, guys. So please make sure you know how to calculate the empirical formula and the molecular formula. Please, guys, that's an easy question, right? Okay, now in 5.1, it says define the term empirical formula. You must be able to define what is an empirical formula. I'm not going to dwell on that. Now it says determine the empirical formula. Right? Determining the empirical formula, guys, you can do it in whatever way you want. There are many ways you can do it on the table, using the table. You can do it in whatever way you want. So let's focus on this way. So it says a 25 gram of a compound with the molar mass of that. Right? So that's the true formula. This is the true formula. Right, this is the true formula. The sample contains 8,0925 of sodium and 5,6425 gram of sulfur and 11,6250 of oxygen. So what you need to do in 5.2, guys, here in 5.2 you need to we were given the sodium. You will say sodium is 2, and then the next one it was a sulfur, and then the next one it was an oxygen. You do the ratio of that. So what are you going to do with this mass? I'm going to convert this mass into number of moles. So write the formula. Number of moles is equal to mass over molar mass there. So you take the mass of sodium, the one that you are given, it's 8,0925. You divide by the molar mass of sodium, it's 23, and the sulfur, it's 5,46. It's 6,425. Divide by the sulfur is 32. And then the oxygen, it's 11,6250. You divide by it's 16. And then you take that and you punch it in the calculator. So when you punch that in the calculator, it will give you the values that guys, I don't want to calculate this. Okay, so it will give you these values. It will give you 1.4, right? It will give you 1.4, and it will give you 0.7, and it will give you 2,8 here. So giving you that, you take the smallest number of moles here, which is at 0.7. So you say you divide it by it. So you say 1.4 divided by 0.7 and 0.7 divided by 0.7 and the 2.8 divide by 0.7. So your answer there, it will be 2, and here it will be 1, and in this it will be 4. So your empirical formula here, guys, your empirical formula here, it will be sodium is what is 2, and the sulfur is 1, and the oxygen is 4. That's the empirical formula there, guys. Your empirical formula. So we are done with the 5.2. It says determine the molecular formula. So when we wanted the molecular formula, guys, what do you need to do there? What do you need to do? You need to in 5.3, is it 5.3? Yeah. The molecular formula, you calculate the N there. You say molecular mass divide, which is this is the true formula. This is the true formula, guys. This is the true formula. Divide by the empirical formula. The empirical formula, right? The empirical formula. So what are you going to do now? You're going to take the molecular mass, which is the true formula. The true formula, which is this one, it's 142. You will say 142 divided by, you need to have the molar mass of this empirical formula, this one. So the empirical formula of this, it's a sodium sulfate. So it's going to be 23 times 2. The sodium, it's 2 of them, it's 23 plus the 32 for sulfur. And then plus the oxygen, it's 4 of them, it's 16 times 4. So the answer here, it'll be when you punch that in the calculator, it will be 71. That will be 71. So you say 142, you take this, you put it here. 142 divided by 71 is going to be no, it can't be 71. It can't be 71. So this is going to be 23 times 2 plus 32 plus 16 times 4. It's 142. So the answer here is 142. Guys, don't assume this is going to be 2. This n is going to be 2. 142 divided by 142. So it's going to be 1. So this n is going to be 1. So the molecular formula now, you say the molecular formula is equal to number, this n times by the empirical formula. So it's going to be 1 times by this empirical formula, which is going to be the same. It's going to be the same. So now the molecular formula, it's what? It's the same. So the empirical formula of this compound, it's the same as the molecular formula. There's nothing wrong with that, guys. Please. Now the last question, it says the caustic soda. The caustic soda is used as a household chemical for drain cleaning. Calculate the composition for each element. The composition for each element, which is, it's a percentage composition, guys. When I say composition, it says percentage composition. So what do we need to do there? The first thing in 5.4, we need to calculate the molar mass of the caustic soda, right? The percent, it's not 2 here, guys, it's 1. It's not 2, it's 1. So it's NaOH, like that. So it's gonna be sodium is 23 plus 16 plus 1. So this is 17. It's gonna be 40 gram per mole, right? Is it going to be 40? Yeah, that's 40. So we're going to calculate the percentage of sodium. The percentage of sodium, you say, you take the molar mass of sodium, it's 23, you divide by the molar mass of the entire, it's 40, we multiply by 100, so it's gonna be 57.5%. So the percentage of oxygen, it's gonna be, the oxygen is 16 over 40, we times by 100, not 100% guys, it's just 100, we times by 100, it's gonna be 40. It can be 40. Okay, it's 40. It's 40%. And then the percentage composition of hydrogen. The hydrogen is what? It's 1. How many hydrogens? It's 1. And then we divide by the total. We multiply by 100. It's gonna be 2,5. Guys, make sure when you edit this, it must give you 100 or 99.99 or 98, whatever value that is closer to 100. I hope this question makes sense. Question 6 is the stoichiometric calculation, the quantitative aspect. Right, now let's look at this. These questions, guys, are possible questions, and if you understand the scale that you apply here, it's gonna make you do any question. Like it says, a pure calcium carbonate powder was dropped into a test tube containing the 0.24 mole of HCl of known volume, of an unknown volume. Now it says calculate the, now it says the following reaction takes place. Calcium carbonate reacts with HCl and gives you calcium chloride, carbon dioxide, and water. Now it says on completion of the reaction, it is found that 1,1 dm3 of carbon dioxide was produced at STP. And guys, this is supposed to be CM3. It says 110 of HCl with a concentration of that is remained in the beaker, right? Now guys, it says here, explain what is meant by the excess. The excess, guys, is a reactant that is left in the reaction. The excess reactant is the reactant that is left after the reaction is complete. So guys, between these two, the calcium carbonate and the HCl, let's say the HCl is the excess. This one is a limiting, that means it's going to be used up completely. After the reaction is completely, there will be nothing that is left in the calcium carbonate, but this one, there will be something that is left after there's something taken from this. The amount, there will be an amount taken from this, which is the amount reacted, and then there will be amount that remained. Now 6.2, it says identify the excess reactant in the above. Guys, it says since this one is a pure, it's a calcium carbonate, it's going to be used up completely, it's going to react completely, and this one is going to be a limiting. So the excess here is the what? It's the HCl. So the answer is the HCl. Now 6.3, it says calculate the number of moles of carbon dioxide produced. The number of moles of carbon dioxide produced. So remember, it says 1.146 dm3 of the calcium carbonate. Carbon dioxide was produced at STP. So the way we're going to answer this in 6.3, we're going to use this formula that says number of moles is equal to volume over molar gas volume. We want the number of moles. The number of moles of what? Of the carbon dioxide that is produced. It's going to be produced because the carbon dioxide is the product. So what are we going to use there? We're going to use the 1 comma, guys, this is also 1 comma, This is also 1,46, 1,46, not comma or not 1,146. It's 1,46, so we're gonna say 1,46 divided by the molar gas volume. It's 22.4, and then it's 22.4. So the answer, when you punch that in the calculator, 1.46 divided by 22.4, the answer is gonna be 0,065 mole, right? So now let's go to the next question, the 6.4. It says calculate the initial number of moles present of HCl present in the test tube. Guys, in order to get the initial number of moles, remember I said here this is going to be an excess. Since it's an excess, there will be a number of moles reacted, and then there will be a number of moles that will be left. And from this one is what is an initial. So from this initial, there will be a number of moles that is going to react, and then after the number of moles that is reacting, there will be something that is left. So they want, what was it initially? The number of moles initially. So we must get the number of moles that is going to react, and we were told the 110 cm3 of the HCl with the concentration of that mole per dm3 will remain. So now we know the number of moles of that will remain, right? But let's get the number of moles that will react first. So how do we know the number of moles that is going to react? Since we know the carbon dioxide that is going to be produced, it can easily give us the number of moles of calcium carbonate that is going to react. So from this number of moles that is going to react, it can give us the number of moles that is going to react, which is that one. And then we can have that one, and we add the 2, and it give us the initial. So what I'm going to do now, I'm going to do the mole ratio. Say the HCl, even if we don't go this route, of this and this, we can do the mole ratio of this and this. So we can say here the number of moles, let's say the number of moles of what? HCl, number of moles of HCl reacted, right? We're going to calculate the number of moles of HCl reacted. So we're going to do the mole ratio. The HCl is to carbon dioxide, which is the ratio here is 2:1. So is 2:1. So we wanted the HCl and the carbon dioxide. The carbon dioxide is 0,065. So the 0,065 we times by 2, and then we cross multiply, right? So the answer x here is going to be 0,13 mole, right? So this is the amount of HCl what reacted. This is the amount of HCl reacted. Remember what we want? We wanted the initial, so we must have the reacted and the excess. Now let's calculate now the number of moles of HCl, of HCl in excess, the one that is going to remain after this amount has been taken, right? All right, so we wanted the initial. So what we're going to do, we were told, guys, here 110 cm3 of HCl concentration of that remained in the beaker. That means this one is what? Is an excess. This is the amount that is what is left, right? So what are we going to do? Let me move this down. Let me delete it. So what are we going to do? We're going to use the formula that says number of moles of what? Of HCl is equal to CV, and then the concentration is 0.09 times by the volume is 110. The 110, it's cm3. You have to divide it by 1000. So you divide it by 1000, is going to be 0.0110. And then when you punch that in the calculator, it's 0.009 times by 0.0110. The answer here is 0.0. I hope I'm punching that correctly. Okay, let's go up a bit. Okay, there are 2 zeros here, and then this is 110. Okay, that's correct. So the answer here is going to be 0.099 what mole. So this is the amount that is going to be in excess there. This is the amount that is going to be in excess. So now, in order to get the initial, you will say number of moles of HCl initial, right? The number of moles initial, guys, it's this amount plus this amount. So you will say the number of moles, which is of HCl excess, or you can say left, plus the number of moles what reacted, which is the number of moles reacted. And this is the number of moles of what? Of HCl left or in excess. That's what remained after there was taken the number of moles of that. Now it's the number of moles reacted in excess. It's 0.00099 plus, and the number of moles reacted is 0.13. So plus 0.13. The answer here it's gonna be 0.13. When you round off that, it's gonna be 1.31 mole. Right? These are the initial number of moles. This is the initial. This is the number of moles that was available when it reacted with this one, and this one was used up completely, and this one there was taken the amount reacted, and the amount left is this one, the one that we're given there. And then the question it wanted in mass, so we're going to use the equation that says number of moles is equal to mass over molar mass, and then we have the number of moles at 0.131. In fact, since we are not done, the answer here it was 0.099 mole. So we're going to say number of moles is equal to mass over molar mass, which is the number of moles, it's 0.13099 equal to mass over molar mass. So the molar mass of the HCl is 36.5. So we're going to say 0.13099 times 36.5. So the mass, the initial mass of the HCl is 4.78 grams. 6.5 it says 5.68 of calcium carbonate was added in the reaction vessel to the start of the reaction. So in this, the mass of this one was added there. So now it says calculate the theoretical yield of carbon dioxide in grams. So the theoretical yield of carbon dioxide in grams, the way you're going to do this, guys, we're gonna calculate it's 6.5.1, 6.5.1. So to get the theoretical yield of this one, we have to convert this into number of moles, which is this amount into number of moles, and we'll do the mole ratio of that. So when we do the mole ratio of this and this, it's going to give us the theoretical. So what are we going to do there? We are going to calculate the number of moles of that. We're going to say number of moles of calcium carbonate is equal to mass over molar mass. The mass is 5.68, and we divide by the molar mass of calcium carbonate is 100. It's going to be 0.0 568 mole. So this is the amount of calcium carbonate reacted. So the amount of calcium carbonate reacted is going to give us the amount of carbon dioxide reacted. Right, it's going to give us the amount of carbon dioxide reacted because of we have this amount. Is going to give us this amount produced, sorry, not reacted, the amount of that formed. Right, so we're going to do the mole ratio, and is 1:1. So the mole ratio will say the number of moles of carbon dioxide is equal to the number of moles of calcium carbonate, because the mole ratio is 1:1. So the calcium carbonate is 0. It's 1:1. It's 0.568 mole. So the number of moles of carbon dioxide produced, it's the same because the ratio is 1:1, but we have to change this into number of moles, so into mass. So we're going to say number of moles is equal to mass over molar mass, which is going to be 0.0568 equal to mass of the carbon dioxide, and the molar mass of the carbon dioxide is what? Is 44. And then when we cross multiply the mass of carbon dioxide, which is this is the theoretical, which is going to be 2.492 grams, which is it's 2.50 grams, right? So now what are we going to do now? We are going to the next question. We calculated the theoretical yield in grams. 6.5.2, it says calculated the percentage yield if the actual yield was 2.25 grams. So in order to calculate the percentage yield, we have the theoretical, and now what we need to do, we use the formula that says percentage yield is equal to the actual yield divided by the theoretical yield times by 100. So the actual we're given there, it's 2.25. That's the one that was done experimentally. So it's 2.25 divided by the theoretical, which is it's 2.50 with times by 100. So it gives us 90%. All right, that's the final answer, the final question of question 6. When sulfuric acid, this is question 7, guys, the acids and bases. When sulfuric acid reacts with water, it ionizes in 2 steps as shown in the balance equation. Here's the first step, ionization. In the sulfuric acid, it donates 1 proton, it's left with 1 proton, and then you take that, you put it in water, you dissolve it in water, and it donates the last proton, it's left with no proton. This is the two-step ionization. Give the Lowry-Bronsted definition of an acid. Lowry-Bronsted, it says acid is a proton donor, right? Now 7.2, it says write down the formula of the conjugate acid of H2SO4 and the conjugate base of SO4. So guys, the conjugate acid of this here, this one, guys, it says the conjugate acid of that. So the conjugate acid of that, so guys, it's gonna be the conjugate acid of that. The conjugate acid of this, write down the formula of the conjugate acid of this. So the conjugate acid of this, guys, if this accepts a proton there, it's gonna be this, right? So here, this one, it acts as a what? As a base, and here it's gonna be an acid. So the answer here for this is gonna be H2SO4, and then the conjugate base for this. So guys, if you're looking at this, Now what is happening here? This one is donating a proton there, so that means it's an acid and this is a base. So the conjugate base for that. So guys, if this one accepts a proton and then it becomes that, so this is an acid and this is a conjugate what? Base. So the answer here is what? Is SO4 2 minus. I hope I make sense for that. Now it says which one of the compound reacts in reaction 1 and 2 are ampholites. Which one are ampholites there? So guys, if you look at this one here, it acts as a what? As a base, and here it acts as a what? As an acid. So the answer here is HSO4, right? It's HSO4, and then no, not HSO4 minus, and then and what? And water, or water here, but water in both cases here, it acts as what? As a base here. Water in both cases, it acts as a base. So the ampholite here, it's this one. So you get the 2 marks for that one. Now it says here, in titration, Elena finds 4CM3 and of a 0.4 mole per dm3 solution of sodium hydrogen carbonate, neutralizes, this is important, 24, guys, this is a volume, this is a volume of a what? This is a volume of a sodium hydrogen carbonate. This is a volume of a base, and this is a concentration of a base. And then neutralizes is very important. In this titration, they neutralize. This is a volume of an acid, and then we are not given the concentration of an acid, right? Now this is the sodium hydrogen carbonate and the sulfuric acid, and it gives us that and that. Now it says 7.4. Why is sulfuric acid is regarded as a strong acid? Guys, it's very important. Now it says it because it ionizes completely. This is a very important question. Completely ionizes completely in water to form or to produce, to form a high concentration of what? Of hydronium ions. Hydronium ions, right? When it's a strong acid, it ionizes completely in water to form the high concentration. If it was a weak acid, it ionizes incompletely to form low concentration of hydronium ion. 7.5, it says how many moles of sodium hydrogen carbonate present in 40 mole of 4. So the number of moles of that, guys, if we're given that this is the volume of this base and the concentration of this base, so we wanted the number of moles in 7.5. so you're going to say number of moles of the base is equal to C, concentration of the base, times by the volume of a base. So the concentration there is what? It's 0.4, and the volume, guys, there, it has to be divided by 1000 to be dm3. 40 divided by 1000, 40 divided by 1000 is going to be 0.04, and then we times that by 0.4. so the answer here of this number of moles of this base, it's 0.016 mole. These are the number of moles present there. Then 7.6, it says determine the number of moles of sulfuric acid that are neutralized by 40 of 0.4 of sodium hydrogen carbonate. So guys, that means, in other words, you're doing the mole ratio. So what are you going to do there? You're going to say sodium hydrogen carbonate is to sulfuric acid, and then the mole ratio there is 2:1. 2:1. You wanted the sulfuric acid, and then we substituted that amount there. So we cross multiply, we're gonna have 2x is equal to 0.016. we divide it by 2, we divide by 2. So the x, when we divide by 2, it's gonna be 0.08 mole, right? This is the amount of what? Of sulfuric acid reacted or neutralized neutralized. This is the amount that is neutralized by this. Then 7.7, it says calculate the concentration of what? Of sulfuric acid. The concentration of sulfuric acid, 7.7, it's C of a sulfuric acid is equal to N over V, right? So what do? Do you have the volume of the sulfuric acid? Yes, we were given the volume of the sulfuric acid. It was 12, right? Of the sulfuric acid, it was not 12, man, it's 24. Then the number of moles, you have the number of moles, it's 0.008. You would divide by the 24. It was in CM3. You have to divide it by 1000 to be in DM3. So you will say 0.08 divide by 0.024. Your answer here, it will be 0.33. So 0.33 what? Mole per DM3. That's the concentration of the sulfuric acid. The last question, the redox reaction. Now it says, consider the balanced redox reaction where a copper and a silver ion gives you the copper ion and the silver. Now guys, between these two, there's a redox, there's a one that transfers electron, there's a one that receives electron. In order to know that, you need to assign what we call it an oxidation number. So let's start with the silver. The oxidation number for silver is going to be 0. The oxidation number for iron, silver ion, is going to be +1 because there's a plus here. And the oxidation number for copper ion is going to be +2 because we have a +2 there. And for this one, it's going to be 0. Now, if you look at the oxidation numbers here, from a copper to a copper ion, the oxidation number increases. That means oxidation occurs there. If you look at the silver ion to the silver, the oxidation number decreases. That means reduction occurs. So that means the one that gives electrons here, the one that gives electrons is the copper. The one that oxidizes, that's copper, it oxidizes to that. And the one that receives electrons, it's the silver ion to a silver. Now define the oxidation. Oxidation, guys, is loss of electrons. That's what you're going to write. It's loss of what? Of electrons. Loss of electrons. Now it says from the balance equation above, write down the half reaction. Reduction half reaction. Which one is reduced? It's this one is reduced to that. So we're gonna write the balance equation. So guys, you need to be careful here. You're gonna start with the silver. You say Ag plus, and then silver, it's plus. That means it gains what? 1 electron. And then it's gonna be what? A silver there. You don't put the 2's there, guys. This 2 and this 2, you don't. Right? Even in the start and reduction potential table, you're going to get it like this, but I'm not going to go there. Now, the formula for the reducing agent. Remember, the reducing agent is the one that loses electrons, and the reducing agent and the oxidizing agent are here. If you're given, this is the net, guys, right? So in the net balance equation, so the reducing and oxidizing, it's here. So the reducing agent is the one, it's the one that oxidizes, which is the one that oxidizes is the what? Is the Cu. So the answer here is going to be what? Cu. So if they wanted the reducing and the oxidizing agent, it was going to be what? Ag plus, right? Not 2Ag plus. Now it says 8.1.4, it says explanation for the answer in 8.1.3 by referring to the oxidation number. So by referring to the oxidation number, we said the answer is copper, but if we look at the copper, the oxidation number increases from 0 to 2. So we're going to say our answer here, we're going to say the oxidation number increases, right? You get the mark from that, and then it increases from where? From 0 to 2, from 0 to plus 2. So we explain according to that. Now guys, when it comes to this in 8.2, you need to pay attention. It says the incomplete chemical equation represents the redox reaction, right? So we have the chromium ion and the iron, and the chromium ion and the iron. Now it says determine the oxidation number of chromium in chromate. It's a dichromate, guys. This is a dichromate, not a chromium. This is a dichromate. So in 8.2.1, so to determine the oxidation number for that, so we wanted the oxidation number of, okay, let me write it there full. It's a Cr2O 7 minus 2. So we wanted the oxidation number of Cr. So what do we do here? Guys, we have this -2. That means it's the net oxidation number for the entire. It's -2, so I'm going to put it there. I will say -2. And we wanted the Cr. And how many Cr? It's 2 of them. I'm going to 2 times. And a plus. When this is Cr, when I'm going to another one, I'm going to say plus, which is the oxygen. How many oxygen? It's 7. And what is the oxidation number for oxygen? It's -2. Oxygen, it's in group 6. So you say 6 minus 8 is going to be -2. So you have 2 Cr. And in this one, it's positive times negative. It's negative 2 times 4, 2 times 7, it's 14. And then minus 2 that side. And then you have 2 Cr is equal to, you have -2 plus 14 there. So the 2 Cr, it's gonna be 12. And then you divide by 2. The Cr is gonna be plus 6. So the oxidation number for chromium, it's plus 6. Now the last question, which is 4 marks, it says use the information on the standard reduction potential table to write the balance equation. Guys, I'm not going to use the table. I'm going to just do it without the table. Now it says clearly indicate the following: the reduction half cell. The reduction half cell here, guys, reduction, this is 8.2.2. 8.2.2, guys. If you are looking here, guys, the question in 8.2.2, the oxidation, reduction, and the balance. So I'm gonna start with the oxidation, guys. Huh? I'm gonna start with the oxidation. Let me rewrite that. We have Cr2 7 minus 2 plus the iron. The iron is 2 plus, and the arrow, it's gonna be Cr3 plus, and then plus the Fe3 plus. Okay, guys, now what do we need to check here? Which one is oxidizing? Which one is reducing? So now I'm gonna write the oxidation half reaction. Oxidation half reaction. Now, what do you need to do? You need to assign the oxidation number. So the oxidation number for this is plus 6, we just calculated, and this is -2, and then this is plus 2, and then this is plus 3, and then this is plus 3, right? Okay, guys, now if you look at the oxidation number here, you have 6 to 3. 6 to 3, that means the oxidation number decreases. That means from Cr to Cr, what's happening in Cr, guys? Basically, we're starting from positive 6 to what? To plus 3. That means it's a what? It's a reduction, because the oxidation number decreases from 6 to 3. And then let's look at the iron. If you look at the iron, what's happening to iron? We're starting from 2 to 3. So from +2 to +3, that means oxidation, the oxidation number increases. That means oxidation occurs there. So what are we going to do? We're going to write the oxidation. Remember, the oxidation occurs here, the reduction occurs here. So I'm going to say F, this is the oxidation half reaction. It's what? Fe2 plus, and then arrow, and then Fe3 plus, right? So if you're looking here, guys, if it has lost, remember the Fe, we said it's oxidizing because the oxidation number increases. You see, it's 2 plus and it goes to 3 plus. That means it has lost one more electron. So we're going to put 1 electron there. That means it has lost electron. So when it's 2 plus, that means it has lost 2 electrons already. And then now it loses another. Here's the another. You're not going to say 3, guys. So this is the oxidation half reaction. Then now let's go to a reduction half reaction. Reduction half reaction, guys, here we know it's gonna be a chromium, the dichromate. It's gonna be this. You write it as a whole. It's Cr2O7 -2, and then what do you need to do here? You leave a gap. I'm gonna show you what we're going to do. It becomes what? Cr3 plus, right? Guys, we need to balance the number of atoms here, right? We need to balance the number of atoms first, number of ions first. So guys, here we have 7 oxygens. So in order to have the 7 oxygens in this side as well, what do we need to do? We have to add 7 water molecules because we have 7 oxygen. So in order to add the oxygen in this side, if we have oxygen, we must have oxygen in this side. So that means I have to add the oxygens by water. That means I have to add 7 water molecules. Now now we have 7 oxygen, oxygens are balanced. Now let's go to this side. Now we have 14 hydrogens here. Do you see? It's 7 times 2, it's 14 hydrogen. In this side we must have 14 hydrogens. So I'm gonna add here 14H plus. I'm going to add the hydrogen ions. Remember, when you add the oxygen, you must add water. When you add the hydrogens, you must add the hydrogen ions. So we have 14 hydrogen and 14 hydrogen. But it is one thing that is not balancing now. It's the charges. So if you look here, we have 2 plus 14, 2 plus 14, it makes what? 12. It's 12 electrons. So if we can do, we can say -2 plus 14, which is the positive 14, is going to give us 12, right? If we go to this side, we have what? We just have what? We just have a 3, but we need to balance. That's another thing that we need to balance. There are 2 chromiums and 1 chromium. We need just to put 2 there, right? So the chromium, that's 2, it's 2 there. So in this side, how many charges do we have? It's just 6, right? It's 6, it's 2 times 3 plus, so it's 2 times 3 plus, which is going to be plus 6. So our charges here are not balanced. So we have plus 12 and plus 6. So that means we have to add electrons. These are the positive. We have to add 6 electrons. So if we add 6 electrons, that means we minus the 6. It's going to be what? 6. And then this side is going to be 6. So that is balanced. Guys, I hope I make sense by that. Now let's go to what we call, it's a net. Now, what do we call it? It's a net. Now, making a net, it says it's a balanced net ionic equation. So the balance net ionic equation, what do? You must have your oxidation and your reduction, but the electrons needs to be balanced. Do you see how many electrons do we have? We have 6 electrons in the reduction. In the oxidation, we have what? We have 1. So that means we have to times this by 6. So when we times by 6, our oxidation now, half reaction, it's going to be, when you times that by 6, it's going to be 6 iron 2 plus and arrow 6 Fe 3 plus 6 electrons. And then the reduction, we just write it as it is. So it's going to be Cr2O7 2 minus plus the 14 hydrogen ion plus the 6 electrons, arrow it's 2 Cr 3 plus the 7 water molecules. And then what is going to happen? This and this and this are going to cancel. So our balanced, now the balanced net ionic equation is going to be, we're going to start with the reactant. It's going to be 6Fe 2 plus, and then we go to the reactants of this one. It's going to be Cr2O7 2 minus plus the 14 hydrogen ion, and then we're done with the reactants of both half reactions. And then we go to product. It's going to be 6Fe 3 plus, and then we go to that, it's going to be 2Cr3 plus and the 7 water molecules. These are the answers. The answer for this one, it's this, and this is the answer, and this is the answer there. I hope, guys, this question, it makes sense. Cheers.